What are we gonna do when she's gone? We just have days every single
Yes.
day.
Are you okay with doing this?
Every single day.
Like, just every once in a while. Like, by that we want buffalo chicken dips, cookies.
There's buffalo chicken dip on it.
Really? Alright.
Apparently buffalo chicken is an Ohio thing too, because like a bunch of people posted about it last night, and then it's like, you guys know about it? How did I not know about it when I lived in Ohio?
No thanks. Okay.
That's true. That's true.
Buffalo chicken dip is amazing.
All right, let's take a look on page 104. I think we have one more example to look at, and then we're going to do a bunch more in the next section, just looking at it a little bit differently, okay? So today's going to be a nice review, I guess, from Friday. I think we're on 11, is that right?
Yes.
Okay, so what we're going to do is we're going to practice writing the rule for the series. Do we remember the difference between a series and a sequence?
Is it the series that has the plus sign?
Mm-hmm. Series is when you add everything. Sequence is just a list where you have the commas. Okay, so since this is a series, you're adding things together. We're going to use that Greek letter sigma, meaning addition or sum. And they want us to write two different rules. Even though it's the same series, we're going to write two different ones. Notice how it depends on where we're starting. So for this, I know. They are very passionate people. All right, so let's think about this one. If we plug in 0 to whatever rule we think of, our first answer should be 1. Then if we plug in 1 into the whatever rule we get here, we should get negative 2/3 as the answer. So this is representing the 0 term, the first term, the second, the third, the fourth. So our upper bound in this sigma would be 4. What would the upper bound in the other sigma that we're going to write? What would that be? 5. Okay, so this is representing the first term, second, third, fourth, fifth. So even though there are going to be different sigmas and different rules, it's still the same series. So let's go ahead and try to find some patterns. Maybe we'll work with this first one. If we plug in 0, we need to get 1. If we plug in 1, we need to get negative 2/3. If we plug in 2, we need to get 4/9. Maybe we notice something about the terms that we can automatically write something in there. Curious what you guys notice or what you think. Mm-hmm. Okay, so we might have, so we're dealing with some type of fraction, right? And all the bottoms are a multiple of 3. Meaning 3 to a power. Okay, so maybe we'll start there. We don't know if this is k plus 1, k minus 1, k plus 2. Okay, we don't really know what the power is, but at least we know we need a power. What about the top numbers? 2, 4, 8, 16. Aren't those all 2 to a power? Right? All right. Maybe we'll start there. Okay, if we plug in 0, 2 to the 0 is 1. 3 to the 0 is 1. 1 divided by 1 is 1. So that one checks out. If we plug in the next integer, okay, whole number, 2 to the first over 3 to the first would be 2/3. If we plug in 2 squared over 3 squared, that'd be 4 over 9. Okay, so it looks like the numbered values are checking out, but regardless of which integer we plug in, we're always getting a positive number. Notice how these kind of alternate. So we need something else in there. Okay, let's maybe multiply by a negative 1 to the k. So if we plug in 0 for all the k's, we'll have 1 over 1 times 1, which is 1. If we plug in 1 for all the k's, we'll have 2 over 3 times negative 1, so that checks out for that sign. If we plug in 2, we'll have 4 over 9 times 1, so that'd be a positive. Checks out. Is there another way we can write 2 to the k over 3 to the k? You can leave it like this, that's correct, but you might see it a different way. Yeah?
I have like in parentheses negative 2/3 and like all of that to the k. Would that work too?
Yes, and here's why. Okay? Take a look at this. If we have 2 to the k over 3 to the k, if both of these are being raised to the same power, you could write it like that, right? Now, how did you write yours? Did you have negative 2 over 3 to the k like that?
Yes.
That would work too, right? If we plug in 0, we get 1. If we plug in 1, negative 2/3. If we plug in 2, we'd have to square this and square that, so this would end up being positive, right? Looks like it's going to check out. So since these are being raised to the same power, it looks like we should be able to multiply these together to get negative 2/3 to the k, if you want to write it that way. You're going to see, though, how when we get to some of these other examples that they're going to separate the negative from the 2/3, okay, in the next section. But it looks like that would be another rule that would work, Autumn, so you could have that too. Okay, so this is what the rule would look like if we start with 0 and we're going to end with 4. How might the rule change now if we want to start with 1? So if we plug in 1, we want to get 1. If we plug in 2, we want to get negative 2/3. Do you see how we're still alternating? So we're still going to need a negative 1 to some power. We don't know if this is a k or a k plus 1 or a k minus 1, but at least it's an alternating signifier, I'll call it. What else can we put in there? Well, let's think about this. This power of k on the negative 1, is it going to stay a k, or do we need some type of plus or minus on there? Either one, right? Because if we plug in 1, we need to get 1. And if we plug in 1 right here, that's going to leave this as a negative value, and we need it to be positive. So somehow if we plug in 1 here, we need to get this power to be 0 or 2. That way this ends up being a positive 1 in the end. So you can have minus 1, you can have plus 1. It doesn't really matter. So we know that power on k should be a little different than at least this one was. Any ideas what else we need here? We still have the 2/3 kind of multiplier showing up, right? But what about its power? Before it was just a regular k. If we plug in 1, we should get 1. If we plug in 2, we need to get a negative 2/3. So is this a k? Is it a k plus 1, a k minus 1? Might have to be a little different. You think it's a minus 1? We'll try it. Okay, if we plug in 1, this will be negative 1 squared, which would be a positive 1. And then if we plug in 1 here, this will be 0. Anything to the 0 power is 1. 1 times 1 is 1. So it checks out. If we plug in 2, we'll get negative 1 to the 3rd, which is a negative 1. If we plug in 2 here, we'll have 2/3 to the first, which is 2/3. -1 times 2/3 checks out. If we plug in 3, we'll have -1 to the fourth, which is 1, times a 2/3, we're plugging in 3, right, squared. So that would be 4/9, which checks out, +4/9. So it looks like this is the rule if we want to start at 1, whereas this is the rule if we start at 0. So notice how the rule changes, even though the series doesn't. Okay, the rule changes depending on where you want to start. Do you want to start by plugging in 0, or do you want to start by plugging in 1? That's kind of what I'm trying to get at with these two examples. Do we see how that changes? Okay, even though the series is the same. Okay? So we're going to do more with series. We're going to get into the next section. Now this section is going to be fairly long. We're probably going to stay on this section until break. Okay? But what we're going to talk about are a bunch of different rules or tests we can use to help us determine if a series converges or diverges. So if we were to go really, really deep and add everything together, would it eventually become an infinity, or would we eventually get a number value? Okay, that's what we're looking at here. I'm not really going to spend much time on this first part because we've already talked about all of that. Okay, we talked about a sub n, how that's the rule. We talked about what a sequence is. Okay, so this is just kind of a general review of the last section we just finished. Okay, we're going to get into some examples. And the first one's pretty simple in my opinion. The sequence, okay, notice how they're being separated by by commas, right? That's a list of numbers. The sequence 2, 4, 6, 8 is a sequence of even numbers. Express the same sequence as a rule of non-negative integer n. So positive integers, 1, 2, 3, 4, 5, 6, whatever. So we're listing 2, 4, 6, 8, and so on. We'll let 2 represent the first term, 4 represent the second, and so on. What rule can we write to represent a sub n? So whatever rule you think of, if you plug in 1, you get 2. If you plug in 2, you get 4. If you were to plug in 3, you would get 6. If you plug in 4, you get 8. Can you think of it? What can you do to 1 to get 2? What can you do to 2 to get 4? What can you do to 3 to get 6? The same rule over, over. Multiply by 2, right? So the rule would be 2n. Whatever term in the sequence you're looking for, you just multiply it by 2 and boom, that's your number. All right, let's try the same thing for the odds. 1, 3, 5, 7, so on. If you plug in 1, you want 1. If you plug in 2, you want 3. If you plug in 3, you want 7. What rule can we have there? Yeah? 2 and minus 1. Checks out. Yep. Those are a little simpler than the other ones we did in the last section, right? So I know in the first example we did, like starting at 0 versus starting at 1, you know those rules change. But I'm going to say most likely, okay, we're going to be starting at 1 in usually every case. So you're not going to have to think about are you starting at 0 or are you starting at 1? Okay, most of the time we're going to be starting at 1 like we did here. So if you plug in 1, you get the first term. If you plug in 2, you get the second. That way it's pretty straightforward. So we're not going to spend too much time worrying about starting at 0. Okay, but what we're going to be doing is we're interested in what happens as we get increasingly larger into this sequence. Okay, are we going to start to see a pattern after a while, or are the numbers going to continue on forever? We're basically trying to figure out, do we converge or diverge? All right, so let's take a look at this first one. They're giving us a rule, okay, a sub n. If we plug in 1, we'd get the first term. If we plug in 2, we'd get the second. So they want us to list out the first 5 terms. And then based off of those, maybe we can see some type of pattern to help us estimate, well, if we were to go really far into this sequence, like what if we were to plug in infinity? Okay, what would we eventually get? Would it converge to a number or diverge to an infinity? So let's go ahead and plug in 1 to get a sub 1. We would have 4 over 5. We'll go ahead and plug in 2 to get the next term. We'd have 8 over 7. If you plug in 3, you'll get 12 over 9, right? Now I know that fraction's reducible, but sometimes I like to leave them unreduced. That way a pattern might be easier to see. Okay, but if you want to reduce it, that's fine. If we plug in 4, we'll get 16 over 11. And plug in 5, we'll get 20 over 13. Okay. So based off those 5 terms, can we think about if we were to keep on plugging in numbers, okay, if our n values were to eventually get larger and larger and larger and larger, what would this sequence eventually do? Do you think we're getting closer and closer and closer to a number? Or are we getting increasingly larger and larger and larger and larger every time, like off towards an infinity? You think it's infinity? Let's try it out. So what makes you say infinity?
Because the difference between the numbers
Mm-hmm.
is getting wider.
So the difference between the 4 and the 5, and then the difference between the 20 and the 13, you're saying they're getting...
Yeah, basically it was less than 1 and now it's greater than 1.
And now it's greater than 1. Okay.
Also, the growth rate from the top looks like it's getting faster than the growth rate from the bottom.
Ooh, I like... So we're going to start looking at growth rates. Now, maybe in terms of those growth rates, if we're plugging in infinity, essentially for this n and this n, does the addition of 3 really affect anything? If you're dealing with very large numbers and you add a 3, are you really changing the value that much? So this 3 really isn't that significant in terms of plugging in infinity. So if that 3 is insignificant, what does 4 over n, or 4n over 2n, simplify to? Isn't it just 2? Okay, so the growth rate is pretty important there. We're going to take a look at a bunch of different examples on the next page with that. But notice how when you look at the powers of n, aren't they both n to the first? Their growth rates are technically the same. Even though you are adding 3 on the bottom, it's an insignificant addition when you consider plugging in large values for n. All right, now if we actually check this out, I mean, this is why I wanted you to use a calculator so we can visually see this. If you did 4 over 5, isn't that 0.8, right? 8 over 7, 1.14, 12 over 9, 1.33, 16 over 11, 1.45, 20 over 13, 1.53, okay, so Eric mentioned earlier that he noticed the difference between the numbers and the fraction is getting bigger, right? But when you take a look at it, those fractions in decimal form, notice how the difference between consecutive terms is getting smaller and smaller, right? So you're actually converging to something. Okay, you're getting closer and closer specifically to 2. Now, it probably would have been better for us to go more than 5 terms in because we want to do really large values of n. Okay, we want to go really, really, really deep. So I would say maybe 10 terms would have been a little bit more obvious for us, but they just wanted us to do 5. A shortcut, though, that we're going to start to look for is that idea of growth rates. Okay, because if we can immediately think about which is growing faster, we can get this much more quickly instead of having to list out every single term. Okay, so let's go ahead and try some of those on the back. We're going to do eventually all those examples with growth rates, but there are just a few things we need to talk about first. The first chart at the top I think is fairly simple to us because we've already discussed these. If we go really, really deep in a sequence and we realize that we're getting infinitely larger, that means we diverge, right? Same thing if we happen to get infinitely smaller. Okay, that's still diverging, just in the negative direction. If we go really deep into a sequence and we find that we're approaching a number, okay, we say that converges. None of that is new to us, right? Okay. What might be a little different is as we go deep into a sequence, if we oscillate between 2 fixed numbers, that one also diverges. I think we saw an example of that last week where we had like 1, -1, 1, -1. Remember that one? Okay. We're not going towards infinity, but we're not approaching a specific number either. So this type of sequence doesn't really fit these 3 options or these 3 possibilities, but it is its own way to determine if it diverges. Okay, but they have to be fixed though, because what if I did 10, -1, 0.1, -0.01, 0.001. Does that one converge or diverge? Are you getting closer and closer to a number, or are you going off towards some type of infinity? That one's converging. So even though you are oscillating, okay, notice how you go positive, negative, okay, this one is still converging. In order for it to diverge, they have to be fixed. Okay, it's the same number every single time. Do you see the difference between the two? Okay. Another thing we're going to have to kind of get used to, especially in this section, are factorials. We've seen the exclamation point before, right? Okay. Now, we know the exclamation point means that we're multiplying all of the previous terms together, but we're not going to be working with numbers so much as we're going to be working with variables, okay, that letter n, to represent which number we are in that sequence. So I'm hoping, if this makes sense, if we have n factorial, we can write that as n times n minus 1 factorial. For instance, if we had 9 factorial, can't we write that as 9 times 8 factorial? Because 8 factorial is essentially 8 times 7 times 6 times 5 all the way down to 1. So here's the 9, and then here's the 8 factorial. Do you see how that's the same as 9 factorial? If we had to, we could go even further. We could do 9 times 8 times 7 factorial. Okay? So they're all equal to each other. So whenever you have a factorial, you can rewrite it using previous terms. And we're going to see some examples of that where it might be useful. Okay? So let's go back and think about those growth rates that Eric mentioned for a second. Do we remember our progression of functions, like slowest to largest, that we did in the improper integral section? What's the slowest growing function, if it even grows at all? A constant, okay? What's next? Natural log. What's next? Okay, we have x to a power. Next we had the exponentials. Okay, was a base to a power. Then we had, that's the fastest growing one. There's one before it. That's the factorial. Okay, so this is what the growth rates looked like in terms of functions when we were working with those integrals. If you were to change the x's to n's, okay, that's what they're going to look like for these rules, because we're working with integer values instead of x values, which could be technically anything. Okay, so determine whether the following sequences converge or diverge. If we were to go very far, okay, into this sequence, okay, keep plugging in number after number after number to get a bunch of terms listed, what would we eventually see happening? Are we going to converge or are we going to diverge? Okay, so in this example, they give you a few terms to at least consider, but they also give you the rule. And I would say looking at the rule is probably going to be the fastest one to help us determine if we can remember those growth rates. So if you think about n going towards infinity, okay, we're plugging in very large numbers of n. Would you say, in terms of this fraction, the top and the bottom are growing the same? Is the top growing faster, the bottom growing faster? What's going on with those growth rates? We might also have to list what happens depending on what's growing faster and what's not. What type of function do we have in the numerator? What type of function do we have in the denominator? There you go. All right, so we have an n to the first up top. Okay, that's x to a power. We also have an n to the first down below. That's another x to a power. If the powers are the same, okay, we have to take the ratio of the coefficients. Now, they're not 0 like I put in there. I'm just circling them because they're both 1. All right, so they're going to, this sequence is going to converge to 1. And maybe you can see that based off the terms. Okay, if we were to plug in very large numbers for n, we would get like 999999999 over 100,000, whatever that was that I mentioned. So you're getting closer and closer to 1 if you were to keep listing out the terms. Right? So let's focus on the rule, but the terms are there to help you if needed. All right, so think about growth rates. What type of functions up top? What type of functions down below? You got to compare them, and then therefore determine what's happening, converging or diverging. What do you think, Caitlin?
Divergent.
How'd you know?
Because it's 1 over really big numbers.
So 1 over something really big. What's that really, really close to? That's 0. Okay. Converges to 0. Yep. If the bigger thing was up top, that would be diverging. All right. Now they give us the rule for the next one, but notice how this rule is not a fraction like the other two were. So it might be a little bit difficult for us to use this growth rate idea to help us. If they give us a rule, though, we should be able to maybe make a list of the terms to help us visually see what's happening here. So let's think about it. If we plug in 1, we'll have 3 minus 1, which is 2. If we plug in 2, we'll have 3 plus 1, which is 4. If we plug in 3, we'll have 3 minus 1, which is 2. If we plug in 4, we'll have 3 plus 1, which is 4. You could do more if you wanted to, but is that enough for us to determine what's happening? Converging or diverging? Diverging. Yep, this is an example of that oscillating one, where you're going back and forth between two fixed numbers. All right, so diverges. Let's check out D. We have a fraction, so maybe we can use those growth rates to help us out. -1/2, good. So growth rate of the top is 1, growth rate of the bottom is 1, those are the same. Divide the coefficients, 1 over -2, good. The next one's a fraction as well. Think about your growth rates. Good, Eric? It does. Okay, natural log is slower than x to a power based off our list here. So the bottom is growing faster, converges to 0. All right, what about the next one? This one's a little tricky. Yeah?
Does it converge to 1?
Possibly. Are you looking at the growth rate? Like this is an n to the first factorial, then you have another n to the first factorial? Is that what you're thinking of? Okay. Converges to 1 is a possibility. Yeah? Converge. Okay. Why do you think converges to 0?
Because you have to add 2 to that, which would change the factorial of that, which would be greater on bottom.
You'd be much greater on the bottom. Okay. So notice how they are both technically factorial functions, right? So they both fit this definition or this setup in our growth rates. But when you take a look at what's being factorialed, okay, the bottom is much larger than the top because you have that x plus 2. If you're not sure, you can always make a list. If you plug in 1 factorial is 1 over 3 factorial, which would be 6, so we'd get 1/6. If you plug in 2 factorial is 2, but then you'd have 4 factorial on the bottom, which would be 24. And then you can keep going. If you're not quite sure based off the growth rates, maybe make some list of numbers and it might be a little bit more apparent. This one is actually going to converge to 0. All right, let's try another factorial. Do you want to make a list of numbers? Do we want to try to do growth rate? Maybe we can rewrite it somehow to see what's going to happen. What do you think? Yeah?
Is it diverging?
It is diverging. Okay, so you could make a list to see that. Here's something else that's worth noting, and we're going to do this a lot in this section kind of towards the end. Let's go ahead and use this box up here, like how we can rewrite n factorial as these different options to help us out with this one. So instead of saying n factorial, we can rewrite n factorial. This is not 2n factorial. Do we realize that? It's just, if it was 2n factorial, they would put parentheses around those two. The only item that has the exclamation point applies to is the n. The 2 is just a multiplier out front. So if this is n factorial, we can rewrite that as n times n minus 1 factorial, 1 less than it. Kind of like the 9 example at the top. And this is all over n minus 1 factorial. Anything going to happen? You see the n minus 1's factorials are going to go away? All right, so this rule actually simplifies to 2n. And if you were to keep plugging in numbers, okay, wouldn't we just eventually list all of the even numbers, which are going to go on forever? So that one's going to diverge. Looks good. Let's try the next one. We can make a list. We can try to rewrite it. Maybe think about some growth rates. Are we listing some numbers? Is that helping? Let's see, if we plug in 1, we'll have 1 minus 1, which is 0, over 1, which is 0. Plug in 2. 2 plus 1, we got 3 over 2. If we plug in 2, or sorry, if we plug in 3, we'll have 3 minus 1, which is 2, over 3. If we plug in 4, 4 plus 1 is 5, over 4. You might have to keep going to kind of see it. What do you think? Yeah?
Does it converge to 1?
It converges to 1. Okay, so you might have to go a little deeper to see it, but let's take a look at this algebraically to see where this is coming from. Whenever you are dividing by one term, okay, we can break up the fraction up top. For instance, this would be n over n plus negative 1 to the n power over n. Right? We can break up the fraction. And n over n simplifies to 1. But notice how this is going to be some constant, because negative 1 to a power is always going to be 1 or negative 1. This is going to be some constant over an infinity value, which is getting closer and closer to 0, right? So 1 plus 0 would give you that convergent value to 1. A little tricky. What about the next one? Maybe write out some terms. Yeah?
Does it converge to 0?
Not quite. Let's see, if we plug in 1, that'd be 0. If we plug in 2, we'd have 1/2. If we plug in 3, negative 2/3. Plug in 4, 3/4. And this would be negative 4/5. All right, so we are oscillating, but they're not fixed numbers. So this could be a converge or it could be a diverge. Are the numbered values getting closer and closer to something? Right? Probably not. I mean, the fractions themselves are getting closer and closer to 1, but notice you're bouncing between like a negative and a positive value, right? So we're not really quite sure. Are we getting closer to positive 1 or are we getting closer to negative 1? We can't say for sure. So this one's going to be diverging. All right, what about J? It's a fraction, so maybe we can do growth rates. Or if you want to list out some terms, you can try that. Yeah? That one converges to 0. Yep, we have an x, or we have a factorial on the bottom, which grows faster than the exponential up top. So it converges to 0. Good. We're going to skip k for a second. We'll do that one tomorrow, because that's a calculator one. Let's go ahead and try L. It's a fraction. Maybe think about growth rates. Yeah? How'd you know? Okay, so what's a little tricky with this one is up here in our list, we said x factorial grows slower than an x to an x. So when you look at this at first glance, you have a slower function over a faster one, which some of you may think is 0, right? Because the bigger one or the faster one's on the bottom. But the fact that there's a 2 being included in the factorial might change some things. Okay, if this was 2n factorial over n to the n, that would converge to 0. But the 2 being included affects it a little bit. Okay, you might have to list out some terms to help you with that. But we'll check that one out probably tomorrow on the calculator too, because factorials can get pretty big. But this one's going to diverge as well. So we'll save all of k and the list of sequence for L tomorrow. Are we doing okay so far? Okay, good.